Hey everyone, Michael Unger here with another Science Fair Foundation workshop. This is workshop number 5, or 5th in our series on STEM-based workshops. This one is analyzing your results. I am here, as you can see, in my kitchen on a beautiful day, actually. Lots of blue sky up there on the unceded territory of the Musqueam, Squamish, and the Tsleil-Waututh. Really excited for you to join us. If you're here in Zoom live with us, drop a hello in the chat. Let us know where you're watching from, and throughout this workshop you can put any questions at any time. This will be an interactive workshop. If you are stepping through the science fair process, perhaps you're at this stage. If you're not quite at this stage, you can save this one for later. Perhaps you're watching later as you've gotten through this stage, but this is a very crucial stage, of course, in the scientific method process. And so we have brought back once again Anne-Marie Simard, a former science fair participant. She's been through this process before, and she's also a member of the Vancouver Island Regional Science Fair Committee. Hi, Anne-Marie. Thanks for joining us.
Thanks for having me. It's a beautiful day out here as well, and I'm really excited to be here and talk about how to analyze our results.
Yeah, for me personally, I'm really excited for this. I actually didn't get to go through a science fair process when I was in school. The previous steps I'm familiar with, but this one I never actually did. And this one seems really exciting. You know, you've done your experiment, you've got your data. Now what is really sort of that next step? So you're going to help us go through some of that. So we're going to start with, reasons for collecting and analyzing data for STEM projects. We'll even go through some graphs and charts on how to analyze and present data. And then, of course, we're going to tell you how to use the data to support your hypothesis. Exactly. So, Anne-Marie, let's get started here and step through this process of analyzing your results.
All right, let's do it. So yeah, maybe just a quick reminder for those who are joining us today. In previous workshop, I think it was workshop number 2, we went over how to plan our experiment. And now that we have all of our data, we're going to look today at the different steps that I would suggest to go through in terms of how to analyze and interpret your information to draw your conclusions, basically.
Well, let's start off with, a really basic question is, why do we collect and analyze data in the first place?
Mm-hmm. Well, the idea is that when we do a science project, we usually start with a question, or we have maybe a prediction or a hypothesis that we would like to be testing. So once we've done your experiment, you actually want to be able to look at the data and figure out, does it support my prediction or my hypothesis, or is it going against what I thought was going to happen? And we want to be able to draw our conclusions as well. So when we do a prediction without data and evidence, that's all it is. It is a prediction that actually needs to be tested and verified. And it's really important to follow a good impartial scientific method to do the analysis in the project, so that the goal is not to prove that you were correct. The goal is to see what the data is telling you, and whatever that is, to analyze it impartially and to come to neutral conclusions and to actually really figure out what is happening there. So based on how your project has been designed, you can actually prove that maybe a prototype is working well with the data that you've collected, or you can find new patterns, relationship between variables or between the topics that you are testing or comparing together. And in some cases, maybe you're going to realize that what you thought was wrong and you've actually discovered something new that was really unexpected.
Do you have any examples, perhaps, from your own experience when you were a science fair participant and you got to this stage? Any interesting revelations that you found as you were analyzing your own data?
I guess maybe more when I was in university, I was working part-time in a lab, and we were working on cancer research. And something that was really neat, we were testing this new drug that was designed for, I think it was breast cancer, and if I remember well, and we were testing it on different types of cell and different types of cancer. And we realized that the drug that we were using was actually really, really good for a specific type of cancer, but not necessarily for others. So the idea here was really to test this drug in different conditions and to kind of figure out, okay, how does this drug actually work? Because we had the drug, we knew it had a good effect, but we didn't necessarily understand how it was working exactly in the cells. And so we did a bunch of tests and analyzed. everything. And we figured out that it was really good for a specific type of cells, but not for others. And that's something that was very surprising for us, but it was really interesting because it helped us push through this drug for other tests afterwards.
Yeah, really interesting. So when you get to this point and you're analyzing data, you're showing sort of like relationships, trends. What are sort of the things that are really the conclusions that you're really getting to after you analyze the data?
Well, it's really the goal, I think, when we're starting with, especially a science fair project, is come back to your variables that you had at the beginning. So when we start a project, you're going to usually test one thing that you're going to be changing, and you're going to observe the effect on another variable or something in particular that you're trying to look at. And when you do your interpretation and your conclusions, you want to come back to those variables and actually finalize and say, is there actually a relationship between these two things? Like when I change A, is there an impact on B? And sometimes we think that a good science fair project has to be highly complicated and very, very complex. But if you're just starting in this, keep it simple, but do a good, solid analysis, the way that we're going to talk about today. And then from there, you can keep continuing your project afterwards. But it's not necessarily about having the most complex result, but it's doing a good analysis of the results.
Yeah, and there's another part to this too that I think has come up recently at large with a lot of scientists, and that's this replication of your data and making sure that when you go through this process that other scientists can understand it so that they can also do their experiment with replicate this experiment, right?
Exactly. And that's something that's really important. And I always tell my students, when you put your data table or your graphs there, or when you're looking at your conclusion, anybody else should be able to read through what you've done and understand what this is about. So when we're going to talk about some of the key components on the graph, for example, but if I just look at a graph, even in the news, everything that I need to understand this information should be on the graph. Sometimes they put on the news, they put a graph and there's no titles or there's no letters on the axis, or you don't really know what they're talking about. And it can be really hard to fully understand and interpret the data properly when you don't have a good solid basis with your data.
And I think that we are all kind of going through some very real life situations when it comes to this. There's a lot of science going on in the news. You hear scientists being interviewed, perhaps sharing data, even raw data with graphs on social media. And, the general public is there reading this and interpreting it, whether on their own, if they don't have somebody else to interpret it for them.
Exactly. And it's, what we've been living through in the last 2 years with all the amount of information coming out in the news. It's been really confusing for a lot of us. And, good science takes time, and it takes a lot of people doing it and testing it and reviewing the information. And to be able to do that properly, everybody needs to make sure that they put all the effort on their analysis and their conclusions to make sure that they're sound, so we can go back and test it again.
Yeah, one of my favorite reporters has actually been using a lot of COVID data, making graphs, is Justin McElroy on Twitter. If anyone's seen how he's been able to interpret data really, really novelly. So let's get into converting data and visually representing this data.
Mm-hmm. Okay, so there's two terms here that I wanted to define just to start that I use a lot in my classes with my students and for science fair too. When you do your experiment, the first thing you're going to get is what we call raw data. So that's just the number coming out straight from your experiment. You haven't changed anything to them yet. You just collect those numbers and you put them maybe in a data table that we've shown in the workshop number 2. So it's direct. It's a bit organized, but you still have to modify a few things to make sure that it's easy to read through and figure out everything. Once you have that, you're going to want to do your analysis, but you need to process your data. So usually when you do your experiment, you're going to test it more than once. So you might have multiple replicates or multiple trials of the same experiment. And then your process data is going to be what you obtained after you've done the averages, or if you have any calculations that you need to do that is very specific to your project. And then you're going to want to put that into a process data table, and then maybe put that into visual representation with some good graphs or charts that you can use. So that's what we're going to be calling the process data.
Okay, so once we've got this process data, what are the types of things that we can do with it?
Well, there's a lot of different types of graph, and we're going to actually walk you through a bit later some examples of what graph can be good in which situation. But this is just an example of a graph that you could see. And I just kind of want to point out a couple of key components here. So you want to make sure that your graph is what I like to call a standalone. So if I just look at this graph, I don't really need to know much about the study that has been done, but I can know that we have the average monthly temperature in Kelowna. So that tells me that each point is that is on this graph is coming from more than one measurement. And I also have both my axis, so the x-axis, which is on the bottom, so the horizontal, and the y-axis, which is vertical, that have a name, so a label. And when necessary, you also have in brackets the unit. So that tells me this is a temperature in degrees Celsius, not in Fahrenheit or in Kelvin. So that's very important in lots of situations to really understand the data. And then in this case, we have two different lines on this graph as well. And they're represented on the right-hand side with a legend or a key that shows us the type of dots or the color based on this is the maximum temperature or the lowest temperature that we've obtained. So this is just one example of the graph. And really quickly here, I can look at this graph and say, from January to December, there's quite a bit of change in the temperature in Kelowna. The highest temperature observed was around like probably 28 degrees Celsius. That would be in July. And then the lowest temperature observed was going to about -5 degrees in January. And then quickly like this, I can pull information out of my graph. And this is exactly what we want to do when we interpret our data.
Okay, so what are some of the, as you get into the stage and you're starting to make graphs, I'm sure if this is a new process for you, you're figuring some things out. What are some pitfalls that happened, some things that you've seen perhaps yourself fall into, or perhaps anyone that goes into this process and starts to make graphs for the first time?
I think sometimes it's tricky because if you're using a software like a spreadsheet, for example, to do your graph, there are other free software online that you can use sometimes, where you can just like type in your data and the website is going to populate for you a graph easily as well. And it's not because it's on a graph that it means that the graph is correct or that it's used properly. And then when we go later over some of the examples of the types of graphs, I can point out more specifically which type is good for which particular reason. But one thing for sure is that if you don't have necessarily numbers, like in this case, we have months on the x-axis, so we can see that there's a progression over time. But sometimes I see a lot of students that are going to try to use any type of graph for their data just because it looks good, but it's not necessarily the best type of graph. So it's important to really reflect on what you're trying to show with your graph. And once you've done it, if you look at your graph and you can't quite figure out what it means just by looking at the information you place on there, then maybe it means that your graph is not done properly and you need to actually revisit how you're doing it.
Okay. Well, now that you've laid that groundwork, let's get into some of the different types of graphs that we can possibly make.
Let's do it. And before we actually go to the graph, we're just going to do a quick review of the experiment that we had done together in workshop number 2, just so that, because this is the data that we're going to use today to make those graph and dose analysis. So let's just refresh our memories a little bit. So we had conducted an experiment to see if baking soda, table salt, or sugar would make an egg float faster or with the least amount of solute when we put a bit of those substances into a glass of water, and we were trying to make an egg float. And then we measured how many tablespoons of each of these solutes we needed to add to the water to have the egg float. Our hypothesis at the time was that we thought that if we were adding baking soda, it would be the one that needed the least amount of baking soda or tablespoon to make the egg float. And then earlier I was talking about variables, and we have the definitions here at the bottom. So on the left, you have what we call the control variables. So those are the things that we kept the same between all of our trials. We use the same amount of water, the same egg size, and we use all the same equipment. And then we changed the type of solutes that we were using, and we were trying to see our dependent variable. So how would the egg actually float, which we could also refer to the buoyancy of the egg. So how well it was able to float in the water.
Now, as I'm looking through this, I'm reflecting back on when I actually stepped through this specific experiment, and there were some errors that had happened in the execution of the experiment. So I'm thinking through. So if I had gone through the process and I had realized I had made some errors, would I continue to going into this stage and create a graph showing the errors that I had made, or would I just not want to include the errors and just go back into the actual data that did, work, quote unquote?
That's a great question. So there's two parts to that answer. My first part would be that if you made an obvious error, like you made an obvious mistake, like for example, you realize that you put way too much tablespoon of salt in your glass, and you forgot to count exactly how many you had, and you're not quite sure. I would just do that trial again if you have a chance to do that. However, if you have an answer that is unexpected, and you're not quite sure why, don't take it out, because you could actually be finding something that's happening, and you don't want to lose that information. However, what I would suggest is that you write down what I call qualitative observations. So those are things that you can see. So as you're doing your experiment, it's good to have maybe a science notebook. We can also take pictures sometimes and just write down, when I did this particular test, I think I might have made this mistake. I'm not sure. I'm going to have to verify. The idea as well is that the more trial you do, so the more time you repeat your experiment, if you do one error one time, if you do the experiment multiple times, when you average all of your data together, that one mistake is not going to have such a big impact on your data. But if you do it just 2 times, then if you make a mistake in the first time, then it's going to have a huge impact on your final result. So that's why we say that it's good to repeat the experiment multiple times. And I would say, unless you can say for sure, this is the mistake that I've done and I know it's impacting my result, I would say keep your data in, but note any doubts that you might have.
Right. And in my case, it was that I was using expired eggs. So perhaps I was finding out some information about the buoyancy of expired eggs, which may lead down, an interesting route if there was something to glean from that information.
Exactly. And then in that case, I would say that's why you want to try to do your experiment early, so that once you've done it and you realize, actually my eggs were expired, then maybe you could redo your full experiment with brand new eggs. And then you could even compare the two at that point, right? And then you add complexity to your own experiment.
Okay, so here, take us through some of the raw data table that you're showing us now.
Okay, so these were our different tests that we have done. So we actually had the baking soda, the table salt, and the sugar. And on the right column, you can see that that was the number of table salt that the number of tablespoon of solute that we added before the egg actually floated. So when it says in trial 1, baking soda 6, that means that we put 6 tablespoons of baking soda in our glass of water before the egg actually floated. And we have multiple trials because we've done this 6 different times. And you have all of the data collected for each of these trials. Now, we want to put together all of the data for the same condition. So we've done the baking soda 6 times. We're going to want to average those trials together to have just one data point that we can put later on our graph. So you have the general equation for the average. Basically, you're going to be adding the values for each of your trials, and then you're going to divide by the total number of values that you had. In our case, we have 6 values. So you can see here in the description, you have each tablespoons added for baking soda. It leads up to 43. And then we're going to divide this by 6. So the average amount of baking soda that we needed to make the egg float was 7.17. And then you would do the same thing for the 2 other solutes or your other conditions. Exactly. Beautiful. Thank you. And then we can really quickly here see, okay, baking soda is at about 7. Table salt is at just under 4, and the sugar is about 10.5-ish. So really quickly with those average, we can see the overview of our results and quickly go to an interpretation or a conclusion. But that was a lot harder to do when we had the 6 separate values. So that's one of the reasons why we process our data.
Yeah. Now, with raw data, we know that we want other scientists to go and look at this information so that they can use it. It may not be something you use in your final presentation, but it is important to have as part of the full package.
Exactly.
And I'm looking at this table, and I'm seeing that it's actually really nicely, there's an aesthetic to it. It looks nice, even if it is quote unquote raw data. It's not just a bunch of numbers and words jumbled together on a page. Maybe talk a little bit about aesthetics, even in the raw data, and how that plays a part.
Absolutely. And again, when you're going to be writing your report for science fair, or when you're going to be presenting, let's say, because it's online this year, maybe a Google slide presentation or a PowerPoint or a slideshow or any way you're going to present it, it's good to have access to the raw data. You're often going to have that raw data more as an appendix, maybe for extra information. And you might just present your process data table and your actual graphs on your slideshow, your final one, on your report. But you want to have that data available for people to go back to and actually look and double check your calculations. For a science fair report, it's rare that you're going to detail all of those calculations, like all the average in your report or on your slideshow. But you want to have that somewhere, whether it's in a spreadsheet that you keep next, like an appendix to your project, or even maybe as a science notebook that a lot of people do by hand. So you want to have that handy to show to the judges or to have to support your information. And it's really important to organize your data to some point before you do your calculations too, not just for other people, but for yourself too. The reason is that it's going to be way easier for you to find if there were any trends or any errors if your data is actually somewhat organized well. If not, it's really hard to go back to and find any mistakes. And if someone goes back and try to figure out, what did they do and how can I do this again to test it? If it's all like jumbled up in a pack and it's really hard to follow through, it's going to be much harder for anybody else to go back and check your results as well.
Excellent. I see we've had a few new people join the workshop. Welcome. We're stepping through analyzing the results. If you have any questions, of course, we're at a very specific stage in the scientific process. We're going through this. You may have a very specific question. Feel free to put that into the chat. We'll have Anne-Marie help you out, let us know what stage you're at, and perhaps you have a problem that you're trying to solve. Right now, we are going to get to analyzing data into some very nice looking graphs.
Yeah. Ooh, beautiful. So there are lots of options for graphs and charts, and it can be really difficult to choose the right one. And what I would say is there are a couple key things that you need to ask yourself. First of all, what's the goal for your graph? Like, what are you trying to show? So what information do you want to put on there? If we're thinking of our science project that we're doing for this workshop, we had two things we were changing. We were adding more solute to our water and seeing if the egg would float. So we basically measured the amount of tablespoon that we needed to make the egg floats for 3 different substances or solutes. So we want to make sure that these two things are going to be on the graph together, because that's what we're trying to compare. We're trying to see, is there a difference between baking soda, salt, and sugar, and how many tablespoons I need to make the egg floats. So that's what we want to have on our graph. That's what we're trying to analyze. So the few options that you have here can be used for different reasons. The bar graph can be really good when you want to compare your different trials together. But you need to make sure that for the bar graphs, the bottom axis, which is the x-axis, usually is going to be categories. So in our case, this is actually a good graph because we're going to have baking soda, salt, and sugar. And on the y-axis, which is the vertical axis, we can have the number of tablespoons. So you see that you have numbers going up, but on the bottom axis, horizontal axis, we have different categories. In the middle, you have a pie chart. Those ones are going to be great to compare percentages or ratios. So the total of what's shown on the pie chart gives you 100 or 100%. So it's going to be, we're actually going to use it in this case to compare the different trials that we made together and see how our results were similar or different between our trials. And the last one is the line graph. And this is very similar to the one that we had with the months in Kelowna with the temperature, except for ours, we had change for the different months. But the line graphs are really good to show a relationship between variables that are both numerical or quantitative. So that means that they give us a quantity. So if you look at this graph, both axes have numbers on them. And that's important because if you don't have numbers on one of those axes, then you're still going to be able to put the data on the graph. And that's kind of what's tricky sometimes for science fair projects, because the data is going to be there. But when you look at it, it doesn't quite make sense because there's no numbers or graduation on those axes. And therefore, you don't necessarily need a line graph. And you might be better to go with a bar graph if you don't have two axes that actually have numbers. And the line graphs are really good to show data that is continuous over a period of time. So if you have time as one of your variables, usually the line graph is going to be really good for that too.
Going through marketing school, and when I got my degree, we certainly went through, in marketing, graphs and charts can certainly be used for manipulation when you're trying to sell a product. There's pros and cons to using charts and graphs. I think the longer that you do it, you can spot things. In your experience, Anne-Marie, what are some things that you have spotted, maybe some pitfalls that people fall into when they're creating charts and graphs?
Sometimes, let's say about the bar graph, because I think it might be the easiest one to look at this point. But let's say that I have a bar graph and my three results are very, very similar. So maybe I have like 6, 5.8, and 6.3. So when you look at the bar graph, you're not going to see a big difference between the bars. They're going to look all about at the same height because they have a very similar result. And a lot of things that people do sometimes is that they're going to change the maximum and the minimum on the axis, on the vertical axis, so that the minimum is like at 4 and the maximum is like at 7. So then now you're going to see a huge difference between your bars. And now people are going to look at this and be like, oh my God, I found something amazing. There's a huge difference between these categories, but really there isn't. So that's one thing to keep in mind. Always check your axis. That's why I was saying earlier, they should have units. They should have a name. Look what the numbers are. Is there a big jump? Sometimes we're going to do a jump because the lowest value we have is like 3,000. So you don't need to have 0 to 3,000 on the graph, but then you still want to make sure that the scale on that axis makes sense based on the data, and that it's not squishing everything in a small zone where it looks like even higher differences.
Excellent. Well, let's move on and let's get into interpreting our results now that we have our graphs.
Yes. So, well, actually now let's do a couple of graphs just to show you. We're going to go over a couple of examples of graphs, some of them that are great, some of them that are not as great for our data, because I wanted to show you some good and bad. So this is the bar graph for this data to really compare our different types of solutes and the number of tablespoons that we use. In this case, I think this is the best that we can use. It's fairly simple. You need a very small process data table on a spreadsheet to do this. You're going to have on one row your different solutes. And then, sorry, I should say in a column, your different solutes. And in the other one, you're going to have your averages. You want to have a great title for your graph. The title of your graph should be very specific to what's on the graph. And just by reading the title, I should have an idea what the graph is without actually looking at the graph. So in this case, we have the average amount of solute added in teaspoons. So I add my units in there to make an egg float in 250 milliliters of water. So even if you have no idea what my experiment was about, just by looking at this graph, you would know what we did or what we're looking at. And then you have on the x-axis at the bottom the type of solute, so baking soda, table salt, and sugar. And on the y-axis, you have the tablespoon. And you could also add their tablespoon of solute or amount of solute with the brackets tablespoon. So those are different ways to do it. And then it's very obvious that we had to add a lot more sugar to be able to make the egg float, but we didn't add that much table salt for the egg to float. So really quickly with this graph, we can see, like, interpret our results. And from there, we're going to draw our conclusion afterwards.
Okay.
Let's go to the next one. Okay, so the next one is actually, it's a different type of graph that's really interesting, but it has a different purpose. So in this case, instead of just looking at, okay, like which solute needed the most tablespoon or the least tablespoon, we're actually going to look at our trials and we're going to compare them together. The reason is when you do your experiment more than one time, the goal is that you want to be confident in your results. So the idea is that if you do your experiment 5, 6, 7, 100 times, if you do it well and you have something solid, you want your result to be the same all the time. So what we do when we have multiple trials is to take a bit of time to see how close to each other my trials were. And if your trials are very far apart from each other, you want to ask yourself why. Is there something in the method that you're not doing the same way every time? Like, are you making some errors? Or are you actually finding maybe there's a process there that you need to look into to explain why your experiment is not the same every time? So what we've done here is that we've actually made a calculation to see what percentage of each amount of teaspoons that we got for our answers we had overall for the baking soda as an example. So for the title, we had how often an egg will float after dissolving 6, 7, and 8 teaspoons of baking soda in the water. And then we can see that for 50% of our trials, which is 3 times, we needed to add 8 teaspoons to get the egg to float. But then in 33% of the time, we actually only added 6 teaspoons, which was 2 times. And then once we actually had only 7 teaspoons that were able to make the egg float. So ideally, in an optimal, like perfect experiment, which by the way never happens because science is never perfect, you're always going to have a bit of an error. You would want to have all the same results for all of your trials. So when you look at your results and interpret those and make your conclusions, you want to ask yourself, how come I've had different amount of teaspoon there to have my same results? Did I go too fast maybe sometimes? Did I not wait enough to see if the egg would float? And these analysis should trigger your critical thinking and your reflection about your experiment and your method.
Okay, so if you have any questions, we've gone through the 2 graphs. Let's get to our 3rd graph and stepping through line graphs.
Yeah, so this one is a line graph. And in this case, I mentioned earlier that it was really good to have a bar graph when we have categories on the x-axis, and the line graph is really good when you have both numbers on the 2 axes. So in this case, we have a line graph with the different trials, and you have the different points that show the amount of teaspoon for baking soda, table salt, and sugar. The problem with this graph is that it shows that there's a line between my categories. So it's trying to draw a linear relationship between my data points when the data points from left to right are actually not related together, right? So we have complete different conditions. So it's actually a bit tricky when you look at it, because you're like, okay, well, it seems like when you move from the baking soda to the table salt, there's like, oh, it decreases and then it increases back when we add the sugar. But really these 3 conditions are separate. Mm-hmm. So we shouldn't be relating those on a line graph like this. However, if we had a time, for example, like how much, I don't know, like what's the temperature outside over time, or like at this time of the day, for example, then you would have a relationship between those time. And then you can try to draw a line to show if there was an increase or a decrease over time. So it's really important when you do your graph that you reflect on it and ask yourself, is this graph actually really showing the relationship that I'm trying to study? Or is it actually confusing and not fully correct? And then you can just change it.
Excellent. Okay, so we've gone through the 3 graphs. Now let's get to how to interpret our results.
So lots of things that we can actually do, but there's a couple of questions that you kind of really want to ask yourself when you're looking at your data. I like to think of analyzing your data or a science fair project in general a bit as a story. So when you first started creating your project, you thought about a problem, something you wanted to solve, or maybe just a curiosity that you had about a question and you wanted to answer that question. And then you did your experiment and now you have your results and your data, and you're trying to figure out what is the data telling you. Okay, so what are you seeing on those graphs? Is there any patterns that you can see? Is there any relationship between the variables that you tested? But beyond that, you also want to ask yourself, what does it mean? So you could tell me, yeah, like the more tablespoon I added, the less the egg was floating or something like that. But what does it actually mean? And why is it happening? You also at some point want to take the time, once you've looked at your graph really well, to ask yourself, what did I predict this? Is this what I thought was going to happen? So is this supporting my hypothesis, or is this showing me that my prediction was actually not what I thought it was going to be? So it did not happen. If you did a project that was more of an innovation, where you created a prototype or build a device and you tested it, you want to look at your result and ask yourself, did this actually meet my design criteria? Like, did I actually create something that do the things that I wanted this device or this tool to be doing? And once you've done that in the context of your experiment, you really want to think ahead as well. So how can I use this information? What do we do with this knowledge now that we have it? And then what else could you go back to change maybe? Like, what would you do differently? So these are all questions that you're going to want to explore as you do your analysis and your interpretation.
Wonderful. And this really does seem like a really crucial part of this stage, whether you have found, positive results or negative results, but interpreting what those are going to mean. So, and there could be a wider interpretation. There could be something that you have found out. You may not know it yet. And that's why, it seems like this stage, you really do need to think through this process and go back and start where you, those initial questions, those initial curiosities, and take a step back and look at the results and interpret what they're really showing you.
Exactly. And one thing too that I find that I love about science fair is that it pushes you to experiment on something that might not have been done before or that you have never heard of before. And I find sometimes in the classroom, a lot of the lab activities that we do are things that, if you do a quick Google search or, your teacher knows what you're supposed to be getting or what is the result typically that you would get for this specific experiment. But the cool part with science fair is that you get to try something where, the answer might not be on Google. And, scientific research, good scientific research does testing on things that we don't know the answer to. So sometimes you're going to do an experiment that has been done before to make sure that you can do a replicate and have the same results. But a lot of the research is actually things that we don't really know what's going to happen. So we can make a prediction. We have some idea, some inferences based on our knowledge of the current scientific literature. But a lot of the time, we don't actually know what those results are going to be. So that's where having a solid analysis and interpretation of your data is key, because you might actually be finding something that has never been found before.
Okay, so we've gone through the process, we've interpreted. Now let's get into a summary of how we can put all of this together.
Mm-hmm. So I'm going to go through this list with you, and then we're actually going to look at an example of a couple of questions that I often ask my students to look at when we're doing lab analysis, and come back then to the egg experiment to sort of see what the answers could look like. So again here, once you have your graph and your chart, a paragraph that summarizes that information. So tell a story using your data. What are you seeing? And really use those numbers, right? We want to refer to the graph, refer to your data tables, really use those numbers into your interpretation. Come back to your hypothesis. Does your data support your hypothesis, or does it not support your hypothesis? And then think of why. Why does it support it, or why does it not? Is there actually a relationship between your two variables? So did changing the type of solute change the amount of tablespoons that we needed to add to the water to make the egg float? Is there a relationship based on your results? Then you want to think of your procedure and your method and reflect back on that. Was your experiment well designed? A lot of the time when you do science, you're going to go through your lab and realize, I think I should have done this differently. Then what would you do differently if you had a chance to go back and do it again? That's one question that I love asking, especially as a science fair judge. I always ask the students, if you could do this experiment again, what would you change? And that's really showing your reflection on what went well, what didn't. And that's what science is about. How can you make it better next time? So again, changes to your procedure that would make it more effective. And also thinking further ahead and what could you do next? So what else would you like to know about this topic? And I often tell my students, if you had unlimited resources and time, what would you do next relating to this experiment? What could you test?
Yeah, really good question. And what we've actually done for everyone is we actually have a worksheet that you can fill out. You can do this on your own time, but we thought that we would show you sort of what the conclusion, what this summary looks like, and we'll even throw up some examples from our experiment of how we summarized our experiment.
So I'm just going to quickly kind of glance over those questions with you, and then we'll switch to the next slide where you actually have the answer, and I can walk you through the key important points there. So this is very similar to what I was talking about on the previous slide, but summarize your results. How do they relate to your hypothesis? Do the results support or contradict your hypothesis? And if you had a tool or a device that you built as an innovation, like, do you actually meet your design criteria? What are the relationship between your variables, if any? Maybe you find that there is actually no link between these two things. How was your project effective at testing your hypothesis and answering your question, right? You had a goal, like, were you able to actually meet that goal by doing this experiment? And if you were to take this project further, what would be your next step and what would you do next? So if we look now at the answers, amazing. You can take time to read through all the details of these answers later, but I want to point out a couple of really important things that are really important for me when I'm looking at these. The first thing, if you look at the summarizing your result box, see those numbers in there? We want to see those numbers in there. So you want to go back to your graph. You've done all these calculations. You've done the averages. Sometimes you might have calculated a percentage change between your conditions. In some cases, if you're doing a physics project, you might actually have used specific equation that you've used to calculate specific amount, I don't know, of the speed of a car or things like that. So go into your graph in your table, use those numbers and put them in there, put them in your interpretation. It's part of the scientific vocabulary. It's part of the scientific terminology. You want to use your units. We want to be able to read this short paragraph and know exactly what you're talking about. So for example, sometimes you read the news and someone is going to say, eating chocolate cures cancer. Okay. And then scientists found that eating chocolate actually helps reduce your risk of cancer. But then when you actually put the numbers in there, you realize, and I'm, by the way, totally making these numbers up right now on the spot, but you're going to realize that you need to eat I don't know, a truck worth of chocolate per week to actually have a good effect on cancer. And when you actually put those numbers in, you're like, okay, well, this is actually not even doable as a human to eat that much chocolate in a week. So I'm never actually going to get a good effect for my cancer prevention, So those numbers make your interpretation scientific. They make them accurate and they make them also in context so that people can actually relate to those numbers and figure out, okay, I need to add 4 tablespoons of salt to make my egg floats versus 300. I'm not going to add 300 tablespoons to my glass just to have my egg float. So those numbers are really important. The other thing is that when you refer back to your hypothesis, you really want to think back, okay, this is what we thought was going to happen. So this was my prediction. In our case here, our results did not support our hypothesis. And then we explain what we thought was going to happen. And then we try to give a suggestion as to why it was wrong or it was not supported. So at that point, you might actually have to do a bit of research. You might not know why it didn't work, and that's totally fine. But then you want to do a bit of research and try to figure out, is there anything out there, maybe in the literature, that I can find that would help me at least suggest an explanation to why I got the results that I obtained. And we don't have it in here, but that's also a place where you want to use your sources and maybe add an in-text citation, or have a list of references at the end that you can go back to and show that you've actually looked out there, if there's anything that could help you explain your results. The relationship between your independent and dependent variables. So again, here, you really want to go back to your graphs and your results and say, as I increase the amount of this, I have seen that this decreases, or this is changing this particular way. You want to be as specific as possible. We don't have it in this box per se because we have it at the top, but again, here, using your numbers could be interesting. Sometimes I have students say, oh, I'm just trying to think of I have some students, for example, that have tested how different testing conditions in school help them have better results. And they would tell me, well, by writing the test in a separate space, the students overall had better results. Well, how much better were their results? Did they have like 3-letter grades over, or were they doing like 1% better? Like, that range in your data is actually important. We want to know how much better, how much change did you actually see? Is it an important change, or is it something that could be attributed to errors? And that's something for more advanced analysis that can be done as well, but you want to at least touch on that reflection and try to figure that out.
Wonderful. Well, Anne-Marie, you've certainly walked us through in a very detailed way how to analyze our results once we get to this stage. If you're here in the workshop and you are in this process, are you at this stage? Are you not there yet? Do you have some questions at another stage? We are blessed to have Anne-Marie here to answer your questions. Please put them in the chat. If you are an educator, perhaps you're supporting some students and they have some specific questions, put those into the chat as well. We'll be here for another 15 minutes. But Anne-Marie, there's a few things that I think that come to mind for me as I'm thinking about this. And certainly it's, resources, if you're doing this for the first time and creating graphs, that might be a bit daunting because there's a learning curve to learning perhaps a new computer program if you haven't used that software before. What are some tips that you might have, certain programs that you think are really easy for an introductory create some graphs type of experience?
Well, the first thing that I would say is first talk to your science teacher and even your math teacher as well. And in a lot of schools, you are going to be learning how to use some tools and software already. So if you can have something or use something that you may actually use in your own classes, maybe next year or in 2 years, but something that you could get comfortable with right away that is going to be for you used regularly after that, that's a good thing to start with. For me personally, I find that Excel or Google Sheets are good options. The reason why is because they're fairly easy to access, but also because there's a lot of resources out there to tell you how to use it. So even if you have an Excel program or any sort of spreadsheet programs at home and you've never done a line graph, you can really easily go on Google or even go on YouTube and be resourceful and just type in, how to do a line graph on Google Sheet. And beautifully in this time, we actually have tons of tutorials that are made for us already on there. So if you're unsure and you don't think you have anyone close by that can help you do that, just do a quick search. And usually those tutorials are really good at showing you step by step how to do these graphs. And then you can save, that reference link, and then you can always go back to it when you're not sure. So that could be a really good option. And I think a lot of people that are great scientists are also really resourceful. And when they find something where they're like, I have an obstacle, I'm not quite sure how to do this, they're going to be looking for the answer and figuring it out.
Wonderful. The other things that I think that I reflect on are when it comes to controlled variables and how that can really trip up your results if they're not actually controlled. And what happens if you get to this stage and you've realized that maybe your controlled variables aren't not so controlled?
That's a common thing. Happens a lot, especially if it's your first time doing a science fair project. And hopefully, if you've done the workshop number 2, we talked about controlling some of those variables. And it's good to actually keep track to see if you've actually done it. You know, I often have students that are just going to list a bunch of things. Oh, I'm going to keep this and this consistent, and I'm going to keep the same temperature throughout all of my trials. And then we get to the end and I'm like, so what was the temperature in all of your trials? And they're like, I don't know. I actually didn't think of recording it, or I didn't really pay attention to it. I just did it, you know, in the same room, but on different days. And I assumed that the temperature would be the same. So then I'm like, well, how do you know for sure that the temperature didn't affect your result? And they're like, well, I don't know for sure. And that's part of your assessment of your own method. And that's something that you can discuss. Now, again, in an ideal world, if you had the time, the money, and everything, you could do your experiment again and control everything. But for a lot of time when we do science, sometimes we have to respect that we have limitations. And this is something that you can discuss in your conclusions and say, you know, I was able to do this and this and this. However, I did not control the temperature. Therefore, there could be some change attributed to the fact that the temperature was not kept consistent. Next time, I will control the temperature by having a thermometer in the room and actually looking at the temperature. So again, science is never going to be perfect, but we just need to acknowledge the limitations.
Right. Yeah, I think that's a good lesson for everyone that's going through this process. Even if it is a bit, even if it is frustrating, but you know, frustrating and results not being what you want, that is actually the process of science, and it's fun if you can spin it that way. Like I said, if you're here in the workshop and you have some questions, please throw them into the chat. We've got about 8 more minutes, but let me tell you about some programs that we have coming up that can support you, because we have a mentorship program here at the Science Fair Foundation BC that you can use a pool of scientists and content experts that you can use if you are at a stage, if you would like someone to help you along. We've got that mentorship program. It's a free program. It runs now until mid-April. You can email questions at any point at your project and get an answer from an expert in your field. We've got that link that's going up into the chat. So I would think that's a highly advantageous program that you should definitely utilize if you're at that stage. Plus, we've got all of the previous workshops that Anne-Marie has referenced, you know, controlling your variables, ethics. You can find those all on our YouTube page, Science Fair Foundation BC. You can also go to the website to find more information about those. And we have a one more coming up, because of course we have communication, reports, presentations, and interviews. So one more workshop that is coming up for you. So check that out next month. But of course, we also have something really fun, Anne-Marie. I don't know if you are an exerciser, I certainly am, but we are sweating for science. And this is Space Edition, something that of course I'm very excited about, being a space educator. So the event dates this year is going to be from May 1st to May 30th. It's a fitness challenge. You can pick your favorite activity. You can walk, you can swim, you can rock climb, log your kilometers. The funds go to supporting programs just like this workshop. And you can have a team. You can have a group of people. You can get your family involved. If you're a teacher, you can get your other teacher friends involved. Lots of fun activities that we can all take part in. Anne-Marie, thank you so much for joining us with this workshop. Do you have any final thoughts, any final tips for people out there in science fairs?
I mean, for me, science fair is really a way to explore a question of your own interest. And I know sometimes in school, we don't get to do that a lot, because a lot of the things we do in our classes are going to be directed or chosen a lot by the teachers. So all I would want everybody to remember is use this opportunity to really explore a topic that you're interested in. And I know, of course, the science fair is often, you know, shown as a competition. Yes, there's prizes, and, you know, you could get great scholarships and participation in other competition afterwards. But just always remember that the goal is really for you to learn something you're really passionate about. And the first time, like, be gentle with yourself. The first time you do a science fair project, it might be really rocky, it might be really difficult, but then that's the goal. Like, you go to the first science fair and then you present your project and you talk with these judges, and hopefully in the next workshop they're going to be telling you how to prep for those interviews. But the judges are really interested, and they're passionate about science, and they really want to know what you've done, and they're going to give you some tips and things that you can improve for next time. And, if you enjoy the process, then come back and do it again next year and try something new. Or you can even use the same project and make it better next year. So just, like, give it a shot and try it and try to do your best and then learn from it. Because that's what scientists do. We learn some information, we stumble, we get up, and we try again with something better. So just have fun with it.
Have fun indeed. Hopefully you have fun with the rest of your school year, Anne-Marie. I know that you're a school teacher, going through and helping to support lots of students there. And if you're looking for more inspiration, we have a podcast where I interview. This season, we've been interviewing past science fair participants. We go back and we learn all about their inspirations, where they got them, and where they are now. And that's Let's Innovate, which you can find on all the podcasting platforms. All right, folks. Have fun out there. Like Anne-Marie said, we will see you here for another workshop next month. Take care, everyone.
Thank you.